Good evening, everyone. Welcome to the NPTEL course, Network Analysis. This is the week one problem solving session of that course, Network Analysis. And week one is about Introduction to Network, Circuit Element, and Sources. I am Teja Golla, a third year research scholar working under Dr. Santanu Kapat at IIT Kharagpur. Let me share my screen. I'm not sure why my video is not showing here. Okay. Yes. So this is week one problem solving session, and it is introduction to network, circuit elements, and sources also. So I am third year research scholar working under Dr. Santanu Kapat, and I'm from IIT Kharagpur. So we'll go to the next slide. So this is just a basic introduction about myself. So myself Teja Golla, and I'm a third year research scholar. I have completed my bachelor's from IIT Kharagpur, and I have converted to PhD, and now I'm a third year research scholar working under Dr. Santanu Kapat and at Embedded Power Management Lab. So if we talk about this course, network analysis, first, before starting with the session, I would like to survey to ask doubts in Swayam portal. So in Swayam portal, there will be this ask a question option when you log into the portal. So there you can ask the question, and the corresponding TAs of the course will be able to see. Or if you have any question, you can ask during these sessions where I'll be answering your queries. And if you have further more queries, you can also mail me. I'm writing my email address. So uh, my email ID is teja2281@gmail.com. I hope you are able to see whatever I'm writing on the screen. Can someone please confirm? Can you see my email ID? Whatever I have written? Yes, sir. Okay, okay. Yeah, so before we go into this session, someone has asked whether you will be providing the link. Yeah, I will discuss regarding that in the upcoming slides. So this course is classified into 12 weeks, as you know. And week one is about introduction to network circuit elements and sources, which we'll be covering today. And in the upcoming weeks, we'll be discussing about the other weeks where solution of linear differential equation with different excitation, and other weeks we'll slowly come into that as you go through the course lecture videos also. And if you solve problems, if you have any queries, then we'll be discussing. But today we'll be discussing about week one only. And these are just a summary of the entire week schedule of this course, but today we'll be discussing week one. So coming to the problem solving session. So first I would like to clarify what we'll be covering in these sessions each and every week. So the plan is something like this. So for the first half an hour or 45 minutes, I'll be revising the relevant theory that is covered in this week one using some solved examples so that the concepts are better understood. After that, we'll be solving some previous year assignment problems, and it is not a one-sided teaching. So I would also ask you to solve the assignment problems along with me, and I would like to be seeing this session more of an interactive session rather than a one-sided teaching. So please interact with me if you have any queries. Don't be shy, even if it's a silly question, please ask. And no question is silly. So even if you have any small doubt, you please stop me at any given point of time and ask me the doubt. Yeah, so for the first half an hour or 30 minutes to 45 minutes, I'm planning to revise the theory and I make you understand the theory better using some solved examples. And after that, we'll be solving 1.5 hour to um, around 1 hour 40 minutes or So 1 hour 30 minutes, we'll be solving these problems. Okay, so there are two sessions. Kindly take a note. And myself, Teja Golla. So every Monday from 6 p.m. to 8 p.m., these sessions will be conducted and it will not be changed. So I have embedded the link of the Zoom meeting of this Zoom meeting, and this link will also be the same throughout this course. And there are two sessions, so two TAs will be taking the same problem solving sessions. And session one is happening on Monday, every Monday, 6 p.m. to 8 p.m. And my friend Calvin Paul Joseph will be taking sessions tomorrow, and his sessions are scheduled to occur on Tuesday, and it will be 6 p.m. to 8 p.m. And his Zoom meeting is different. So kindly take a note. So this is link two, and this is link one. So these two are two different Zoom meetings. So I will be conducting my sessions in my Zoom link. So this is my meeting, and the meeting will not change. All the problem solving sessions will happen in the same link. So you keep try to save that link so that you can join the meeting. And this will happen tomorrow, and this will happen in every Tuesday. And it is not mandatory to attend both the session. If you are busy on Monday or if you are occupied on Tuesday, you can try to attend any one of the session. But if you are interested or if you're having some more doubts, then you are requested to attend both the session. But it is not mandatory to attend both the session. You can choose any one of the session, or if you want to attend, then you can attend, but it is not mandatory. Kindly take a note. Okay. So all the lecture videos, whatever we are conducting in these sessions, all these 12 weeks, all the problem solving sessions will be recorded. So we are recording these sessions and it will be uploaded to our respective YouTube channels. So I will be uploading it to my YouTube channel. So I have embedded the link to this text. Also, I will be sharing whatever I am teaching in every session. I will be uploading that notes, what are slides or a problem, what are problems that we have solved. All the notes I will be uploading it to my Google Drive, and the link to the Google Drive is here. So this is my YouTube channel link. Just a minute. So this is my YouTube channel link, and this is my Google Drive. So you kindly save all these three links. First of all, the Zoom meeting link to access or to enter the Zoom meeting, and my YouTube channel link where I'll be uploading all the lectures. I will be creating a playlist for this course. Last semester, I have taken another course, which is digital control in switch mode power converters and FPGA based prototyping. So I'll also be uploading these lectures also in a different playlist. So keep this link available with you, so you can directly access these videos directly from there. And lecture notes, all my week 1 to week 12, all my lecture notes, all my PPT, if I have made any, and all the problems that we have solved, all will be uploaded to my Google Drive. I have made a folder, and within that folder, I'll make week-wise subfolders, and I'll upload individually to all those weeks, and you can download it from there. And if you are not, or if you are facing any issue, and if you are not able to access it, kindly revert me back. Uh, I'll clarify your doubts. Okay, someone has asked, kindly put these links in the chats. Yeah, let me do it. Okay, so the first link, let me go here. Okay, so this copy link. So this is a Monday meeting link. Okay, so this is Monday meeting link, and this is Tuesday meeting link. Okay, and now I will be sharing my YouTube channel link. And this is my lecture notes link. Currently, I have not uploaded any notes in my Google Drive, so it will be empty. But after this session, I'll be uploading all these PDFs. I'll not be uploading PPT. I'll be uploading corresponding PDFs. I hope till it is clear. If you have any doubts till this point, you can ask.
No links given in chat box, sir.
I have
No links.
no links.
I have not no links in chat
Okay,
box.
okay, okay. I'm sorry. I think I have sent to a particular person. I'm sorry. I am sending it again. I have replied to a one person. Let me- Okay. So this is Monday meeting link. Just let me know if you have received the link in the chat box. Can anyone please confirm?
Yes, sir.
Okay, okay. Thank you. And
Yes, sir.
this is the Tuesday meeting link. Did you get the Tuesday meeting link? Okay, and this is my YouTube channel link. And this is a link to my Google Drive where I'll be uploading all the notes. Okay. Just kindly confirm, someone of you, please confirm if you can, if you are able to access all the four links. I have mentioned four links, two links for the two Google meetings and one link for my YouTube channel and one link for my Google Drive. Currently, you will not find any notes in there because I have not uploaded, but after this session, I'll be uploading. And kindly take a note, our sessions will be happening on Monday 6 to 8 and I'll try to upload it by Tuesday. So I'll be uploading the videos. By Tuesday night or maybe Tuesday evening, depending upon the size of the video, because after conducting this session, I have to merge the videos and I have to process it and it will take some time. So by Tuesday, every week I'll try to upload it and you can access it from there. If you have any queries, you can mention in the comment section and I'll try to reply within 24 hours or so. And link to the Google Drive also. This also I'll be uploading by Monday if possible, or maybe by Tuesday. So by Tuesday, you will get the link to both the lecture video, also the lecture note. Okay, so this is just a basic introduction about how this meeting happened and where to access it. And tomorrow you can ask Calvin Paul Joseph regarding the link to his Google Drive as well as the link to his YouTube channel. So if you can directly access the videos. And also I'll provide the link in the description of each video, so you can access it from that video itself. I'll be mentioning in the comment section the necessary detailed structure, timestamps, everything, so you can access it better. So this is just the introduction. So before we go into the technical part, if you have any queries regarding this session, you can ask. And one more thing, just to add. So there will be 12 weeks, 12 weeks, and each week I'll be taking 2 hour problem solving session. And additional to that, 1 hour problem solving session I'll be taking at the end just before exam. Before your final exam, I'll be taking a 1 hour session, just like a revision, or if you have any queries before going to exam, we can discuss them. So I'll be taking 12 into 2 hour session, 24 hours, and plus 1 hour before exam. So if you have no more queries, then we can go to the technical aspect of this thing. So let me open the lecture notes. Yes, yes, okay. are you able to see my screen?
Yes, sir.
Okay. So have you first of all have you gone through the lecture videos of whatever is covered in this course till week 1?
Yes.
Okay. And what is covered?
Basically, KVL and KCL.
Okay. Yeah. So in this week, sir has mainly covered about KVL and KCL. So it is just an introduction to circuits and circuit elements and the sources. So what type of sources are there mainly? So how many sources? What type of sources are there? Voltage source and current source, right? So sources are basically two types. One is the voltage source and the other one is the current source. So in the voltage source, the voltage is constant and you can draw any amount of current, and the current source, the current is drawn and the voltage across the current source can be anything. What I mean to say is, say we have a voltage source and the voltage V is fixed and the current I can be anything. It can be 0 amperes or it can be 10 amperes, but still the voltage of the voltage source is fixed. Whereas in the case of current source, it is drawing or it is supplying a fixed amount of current, and the voltage across the voltage source can be anything. Even if it is 0, it still supplies the constant amount of current, and even if the voltage is 10 volt or 5 volt, the current that it is supplying remains same. So these are about the voltage and current sources. And later SAR has also explained the mesh analysis and nodal analysis, where you will be using KVL and KCL. So it is basically used to solve a given circuit. So before we go into mesh analysis, so can someone tell me like which Kirchhoff's law we use in mesh analysis, and which Kirchhoff's law we use in nodal analysis?
KVL in mesh analysis and KCL in nodal analysis.
In mesh analysis, KVL, and in nodal analysis,
Nodal in KCL.
yes. So in mesh analysis, we use Kirchhoff's voltage law, and in nodal analysis, we use Kirchhoff's current law. What does Kirchhoff's voltage law says?
Sum of voltages in a loop is 0.
Yes. So if we consider any mesh in a given circuit, and if we go around that mesh, and if we say this is a given circuit, and we have started from this point, and we have considered this small mesh. So I am considering this mesh. Say, and if I'm starting from this point, and if I reach this point again, the potential difference will be 0. So and that is what KVL is all about. And yeah, so there are different number of meshes, so we have to identify the meshes in a given circuit. Here there are 3 meshes, so we have to apply KVL in each of these 3 meshes, and by applying that we'll get 3 equations, and there are 3 unknowns, mainly I1, I2 and I3. So before we start, let us just consider this circuit and apply KVL. Okay, so let me copy this into my notepad. And another thing, I'm using the Zoom normal session. So each meeting will end at 40 minutes. So after 40 minutes, the meeting will end, and I'll start the meeting again. So in the same link, you please try to join. So as this is a 1 hour 20 minute session or 2 hour session, there will be 3 such meetings. So after 40 minutes, the meeting will end, and then we'll again rejoin. And after another 40 minutes, the meeting will end, and again we'll rejoin. Okay, so here we have 3 meshes. Say this is mesh 1. Okay, let me use a different color. Say this is mesh 1, and this is mesh 2, and this is mesh 3. So can someone tell me, if we apply Kirchhoff's voltage law in mesh 1, what will be the equation? Say we have considered from this point. From this point, if I go around this mesh and if I come back to this point again, what will be the equation?
For mesh 1.
Sorry.
E1 minus E2 minus R2 R1 minus R3. Right.
Okay, so one certain way is, first of all, before we start with any mesh analysis, the main assumption is, yeah, someone has mentioned in the chat box. Yeah, it is correct, I guess. Okay, let us check. So before we start with any mesh analysis, first we have to assume the current direction in the mesh. So it would be good if you follow the same notation throughout this course. So here I am considering clockwise. So in all the meshes, I'm considering clockwise direction. Maybe the current is in a different direction, then we'll end up getting a negative value, but the convention is same. So here I'm considering I1, here I2, here I3. So we can apply the mesh analysis, but a simple trick is, say we will get an equation in this format, right? A into I1 plus B into I2 plus C into I3 is equals to some voltage V. So if we are applying in the mesh of I1, the I1 coefficient is sum of the resistor in that mesh. So A will be R1, R2 plus R3. So A is R1 plus R2 plus R3 into I1. And for the other currents, the resistance common, the resistance that is in common between these two meshes is the coefficient of those particular currents. What I mean to say is, here I1 is there and here I2 is there. So I2 and I1, they have a resistor in common, which is R3. So the coefficient of I2 is R3 with a negative sign. So within that particular mesh, if we have I1 coefficient will be positive and the other coefficients will be negative. So among I1 and I2, R3 is shared, or I1 and I2 both are passing through R3. So the coefficient of I2 is R3 with a negative sign. So we'll have minus R3 into I2. And similarly, what will be the C value in using the same logic? Hello.
Minus I3 into R2.
Yes. So it will be minus R2 into I3. Now coming to the voltage, we have to check. So within that mesh, whether if there is any voltage source, whether that is providing the current or whether it is taking the current. So here E1 is there. If it is supplying the current, then the current direction should be like this. But I have considered the current in a way that it is entering the source. So the convention is, if the if the source is supplying the current, then it is positive. If the source is taking the current, it is negative. So so here, whether the source is taking the current, so whether the source is taking I1 or whether it is supplying I1 in this particular mesh.
It is taking.
Taking, so it will be negative, minus E1. Okay, so now we'll go into the mesh 2. So this is about mesh 1. So mesh 1 is done. Now we'll go into mesh 2. So mesh 2 has again I1 coefficient, I2 coefficient, and I3 coefficient. Okay, so what is I1 coefficient? I1 coefficient is the negative of the resistance that is shared among I1 and I2. So someone has mentioned in the chat mesh 2. Yes. Yeah. Yeah. You are right, Pawan. So this is for mesh 1. So I'm writing mesh 1 as M1. So for mesh 2, M2, we want I1 coefficient. So I1 coefficient is nothing but negative of the resistance that is shared among I1 and mesh 1 and mesh 2. So what is shared among M1 and M2? Resistor R3 is shared. So the coefficient is minus R3 into I1. And for I2, which is the current in that particular mesh, it will be the sum of the resistors. So what will be the coefficient of I2 in mesh M2?
R3 plus R4 plus
R5,
I5.
yes. So R3 plus R4 plus R5 into I2. And what will be the coefficient of I3?
Minus
I2
R4
minus I1.
Coefficient of I3. Minus R4. Yes, because R4 is shared among mesh 3 and mesh 2. So the coefficient of I3 will be negative of that resistance. It is minus R4 into I3. And so whether so the only voltage source in this mesh is E1. So the polarity is dependent upon whether that direction is as if it is supplied by the source or whether it is taking. So whether E1 is supplying the source or whether it is taking the current.
Supply.
Supplying. So it will be plus E1. And this is mesh 2 M2. So now we'll go into mesh 3. I'll use some different color. So mesh 3 has again AI1 plus BI2 plus CI3 is equals to V format. And here what will be the coefficients of I1, I2, I3? So I1 coefficient is the resistance shared among mesh 1 and negative of the resistance shared among mesh M1 and mesh M3. So it is minus R2 into I1 minus R4 into I2, and then sum of the all the resistors, which is R4 plus R6 into I3 is equals to the voltage. Again, whether it will be plus E2 or minus E2.
plus R2 also.
Sorry.
R2
R2,
also.
R2. Yes, yes. Yeah. Thanks for pointing it out. So it will be R2 plus R4 plus R6 into I3. And on the right hand side, whether it will be plus E2 or minus E2.
Minus E2.
Minus E2. And this is for mesh M3. Okay. Minus it. So now we have three equations, three unknowns, and I'm not sure whether you are allowed to use calculator. So if you are allowed to use calculator, you can directly plug in and get I1, I2, I3 values. And according to the question, whatever is asked, if they are asking any power dissipated, so from this I1, I2, I3, we can solve the remaining part. But if you are not allowed to use calculator, then you have to substitute one of the equation in another equation and reduce it to two unknowns and then again solve it. Just a heads up, there is less than a minute. After this minute, the meeting will be automatically closed. Then I will again rejoin. So you kindly rejoin there. So then we can continue our discussion. Till this point, if you have any query, you can ask before we move on to the next topic. Sorry.
Sir, could you hear me?
No query.
No, sir, actually, only the plus even in the first equation.
Why is there?
Because according to the equation, total sum of gain equal total sum of, gain and loss should be equal to 0. Then actually the current is flowing from positive and negative terminal.
In which
It should be plus even.
in which mesh?
First equation.
First equation. Okay. What is your query? If this meeting end, kindly rejoin. It is less than.
Yes, sir.
Okay.
Are you audible?
Okay. Yeah. Someone was asking the question. Can you please continue? Hello. Someone was asking a question regarding mesh M1.
So the I1 current through the cell E1 is entering to the positive terminal and leaving to the negative terminal.
Yes,
So
yes, yes.
then according to the equation, minus I1 R1,
Hmm.
sorry, minus I1 into R1 plus R2 plus R, sorry, I1 R, oh, okay, sir, I got it.
Okay, okay, okay. So let me just repeat that logic again. So the logic is, if you are considering any mesh, say here there are three meshes, M1, M2, M3, and we are applying KVL in a mesh M1. So the left hand side will be the summation of the currents with their coefficients, and on the right hand side we have voltage source. Okay. So each of these coefficients, we can directly get it from the circuit without writing any equation. How I'm telling. So if we are in the mesh M1, then the coefficient of I1 is the sum of the resistors in that mesh. So here in mesh M1, we have R1, R2, and R3. So we are directly getting the coefficient as R1 plus R2 plus R3. And the coefficient of I2 or I3 is given by negative of the resistance shared among M1 and that particular mesh. So if I'm talking about B, so I'm talking about I2. So I2 is in mesh M2. So B is nothing but negative of the resistance that is in common among M1 and M2, which is R3. So the coefficient is minus R3. Similarly, the coefficient of I3 is the negative of the resistance that is in common with M1 and M3 meshes, which is R2. So minus R2. So this completes my LHS side. Now coming on to the RHS side, which is the voltage sources. So in the voltage sources, it could be either positive or negative, but how will I know whether it is positive or negative? So if the current is as if it is entering the voltage source, it is negative. If the current is as if the current is coming out of the voltage source, then it is positive. What I mean to say is, if we consider this I1, the mesh M1, I1 is entering the source. So we'll get minus sign. So that's a minus E1. Whereas if you consider mesh M2, the current is as if it is coming from the source, as if the source is supplying the current. So it means it is positive. So that's why we have plus E1. Even in the case of M3, the current is entering the source. So that's why we have a negative of E2, and that's why we have this minus. So I hope till this point it is clear. Hello.
Sir, will you
Yes.
discuss about Kramer's rule to solve these equations?
Okay. But are you allowed to use calculator in the exam, or you are not allowed to use the?
We are not informed about this. Not
Okay.
know, don't know also.
Okay. Okay. So one way is to do the inverse of the matrix, but I'm not sure. So let us not waste time on that. I'll talk to the corresponding authorities and I'll get back to you next week, or maybe I'll inform the TA tomorrow to discuss regarding that. But I'm not sure if you are gate calculators are allowed. So then if you want to use calculator, then you can use. I use this scientific calculator. There are new calculators which can solve up to 4 equations. So yeah, so in that equation you have to directly plug in the coefficients and it will solve, and it will directly give I1 and I2 and I3. But if the calculators are not allowed, then we'll discuss about online calculations. I'm not sure whether you can do online calculations in Gate, but as calculators are allowed, you can use calculators. But I'll get back to you. I'll check and then I'll let you know if they are not allowed. We'll discuss about how to solve it. Yeah. So this is one. Okay, so this is the mesh analysis. So let me just put a heading. Okay. Now we'll go into nodal analysis. Will we be discussing about dependent sources? Yes, yes. Dependent sources, they are not covered in this week, so it will be covered in the upcoming week. So if you are not aware about dependent or independent sources. So independent sources are like, say we are talking about independent voltage source. The voltage of that source is independent of any other element in the circuit. Say I'm talking about 5 volt voltage source. So the voltage source of the voltage of that source is 5 volts, and it is fixed. Even if you connect it any circuit, it is fixed. Whereas if we discuss about a dependent voltage source, there the voltage of the source is a function of some other element. Say, let me take a quick example. Say we have a circuit like this. So normal independent voltage sources are represented by this circular notation. Say this is 1 ampere, and here I have 1 ohm, 2 ohm, and this is 3 ohm. And the if I use this square, not exactly square, this rhombus type of notation, it means it is a dependent source. So when I say dependent source, it is dependent on some other value. Say here the current is I, and this could be 5I. So the voltage of this source is a function of current in this branch, and it is 5 times of that current. So now I have to consider this as 5I, and I have to write whatever KVL or KCL equation, and then I need to solve for I. Whereas if you consider this 1 ampere, irrespective of whatever circuit I am connecting here, this is still 1 ampere. So it is independent source, and this is dependent source. But if you have still some confusion, sir will be discussing in the upcoming lectures. So there you can understand it better. And if you are still facing issue, then in that particular problem solving session, we can discuss. Okay, so before we go into nodal analysis, let me take a snip of nodal analysis. So here we have some circuit. Please explain super mesh. Okay. So here we have considered 3 individual meshes. And within a mesh, there is no other mesh. What I mean to say is, if I consider this small m1, there is no m1. Like there is no other mesh in that m1. Whereas if I consider this mesh m2, there is no another mesh inside m2. Whereas if I consider this m3 mesh m3, there is no such another mesh. But if I consider the outer mesh, there are 3 meshes inside that mesh. So whenever we do mesh analysis, we usually do not consider a mesh within which another mesh exists. So we have to consider those meshes within which no such another mesh exists. So if I consider this outer mesh, there are 3 such meshes inside, right? So we should not consider that. But sometimes the meshes are in such a way that we run out of equations. Like we'll be having 3 variables, but from the meshes we'll be only getting 2 equations. Then we have to apply KVL for another mesh to get another third equation, say for the outer mesh, which we call as super mesh. So when we solve few problems, then I'll be solving one of the problem where we'll be getting 2 equations from the 3 meshes, and then we have to apply another equation to get 3 equations as there are 3 variables. So we'll get into that part when we solve the examples. So now this is nodal analysis. So in the nodal analysis, the yes, so yes. So we use super mesh if there are like if there is a current source among 2 meshes. Okay, let me quickly consider an example. So what happens if there is a current source? So I'll be considering the sorry. So I'll be considering the same circuit, but I'll be considering a current source. So if there is a current source here, so when we apply KVL or when we apply mesh analysis, what we need to know is we need to know the voltage across each element, because this is basically KVL. So we can only apply KVL when we know the voltage across each element. But if there is a current source, then we do not know the voltage across the current source. So I cannot apply mesh analysis in these two meshes, right? So in this and in this mesh, I cannot apply mesh analysis because I don't know the voltage across this source. But I know that, say, this is I1 and this is I2 and this is I3. I know that I1 minus I2, say this is small I. So I1 minus I2 is small I. So I know that I1 minus I2 is small I. That is one equation. And this is a mesh M3. So in mesh M3, I'll apply KVL. So whatever I have applied here, I'll be getting another equations. So how many unknowns I have? I have three unknowns, I1, I2, and I3, but I am only getting two equations. So I need another equation, but I cannot apply KVL here because I do not know the voltage across this current source. Then we apply KVL in the outer mesh, and then we'll get another equation. And then we'll get another equation, and then we'll solve three equation, three unknowns. So basically, if there are three unknowns, we need three equations. So if we are not able to get those equations by the conventional way, then we have to see some other loops where we can apply KVL or KCL in the case of nodal analysis. And then in that case, we'll be getting another equation. Same problem exists in the nodal case. So in the case of KVL, if there is a current source, we do not know the voltage. Similarly, in the case of nodal analysis, if there is a voltage source between two nodes, we know the current that it is supplying or taking. So there also will be facing the similar issue. One easiest way, Sir has, I think, considered transforming the equation into a different equation. I mean, the circuit into a different circuit to apply. But I would rather suggest, like from my experience, you can see of any other nodes or any other loops where you can apply KVL or KCL to get that extra equation. Because for solving three unknowns, we need three equations. So you can see from where you can get that third equation so that you can solve. So now let us take this example where we have A, B, C nodes and O. So when we apply nodal analysis, we are free to choose any node to be a ground. So I can either choose A to be ground, B to be ground, or C to be ground, or O to be ground. So for my ease, I am considering O to be ground. So this I have considered ground. So in nodal analysis, we'll be applying Kirchhoff's current law. So Kirchhoff's current law says any amount of current that is entering a node will also be leaving. So here I am free to choose current directions. So I'll be randomly choosing some current direction. Say the current direction is here like this, like this. You are free to choose because at the end you might be getting a negative value of current, which means you have taken the opposite direction. But you are free to choose any direction. So I'm considering. First, I'm assuming current direction. So now I have assumed current direction. So now I'll apply Kirchhoff's current law at node A. So node A, sir, can you please explain briefly about what is a branch, node, and loop? Okay. So node is like a junction. So node is a junction of three such branches. So like, let me use a different color. So this is a branch. And node is a connection of more than two such branches. Say here, if you consider this point, this is not a node because it is not a junction of more than three branches. But A is a node because it is a junction of three branches. This branch, and this branch, as well as this branch. And a loop is like A loop is first of all, a loop is a closed loop because it should be closed. It is not open. Like if I consider this R1 and R2, this is not a loop. First of all, a loop should be closed. So when we traverse across that loop, say we have started at a point A and we are traversing across that loop, we should again reach A, but not more than once. What I mean to say is, let me use a different color, say pink color. Say this is a loop. Okay, so I'm starting at A and I am reaching A again, but I'm only touching A, like I'm starting at A and I'm reaching A. In between, I'm not touching A. So what I mean to say is, like, okay, I think I should use a different color, else it will be confusing. So let me use some green color. So say I have started from A and I'm going like this, like this, like this, like this, like this, and like this again. Now this is not a loop. I'm starting at A, I'm reaching at A, but in between I have touched A. So that is not a loop. A loop is only that part where we'll only be starting at a point and we'll be reaching that point without touching it in between. And it should be a closed path. Okay, so yeah. Now I'm applying KCL at the point A. So the current that is entering A is equal to the current that is leaving A. So from how many branches the current is entering? From only one branch, the current is entering, and from the other branch, the current is leaving. So how will I know what is the current that is entering? Can anyone tell me? So I am saying okay, let me use black color. So I entering is equals to I leaving, right? So the current entering is through this branch and current leaving is through these branches. So how will I know what is the current that is entering?
A minus E2 by R.
Okay. You are partially right. Branch has many elements like RLC with voltage or current source. Node is a junction where two or more elements will be connected. Loop means closed path. Yeah. Yeah, you are right. Found. Yeah. So say this is my voltage VA. This point, what is my voltage? It will be VA minus E2. Right. Say I have assumed the current is flowing like this, and this terminal is VC. So that voltage of the terminal, two terminals of R6 are one is VA minus E2 and one is VC. As the current is flowing in this direction, so by my convention or whatever I have assumed by my assumption, I have assumed that VC is at a higher potential compared to VA minus E2. So the current will be higher potential minus lower potential by R6, that resistor R6. So now the current is leaving in two different branches. Okay, so one is this branch, R1 branch, one is R2 branch. So in R1 branch, what is the current? Hello. In the R1 branch,
VA
what is?
by R1.
Yes, VA by R1. And in the R2 branch?
VA minus.
VA minus VB. Why not VB minus VA?
Because we are considering A as a point.
Okay.
Considering VA as a higher potential.
Yes, yes. So first we have assumed the current direction, which will fix the voltages, like which is higher or which is lower. So someone is asking, can you please explain the current entering? So this is the branch that is entering that like the current in this branch is entering the VA. So I need to know the current in this branch. So for getting a current expression and knowing that there is a resistor in the branch, I need to know the voltages of the two terminals of the resistor. So I need to know this voltage, I need to know this voltage. Then I know that VA minus VB by resistor will give me the value of current. I know that this resistor is at VC. It is an unknown and I have assumed that it is VC. So that is known. This is VA and this is E2. So if this is VA and the E2 potential is, say, this is my VA, and this is my another terminal, and this is E2 plus minus. So plus will be at a higher potential. So whatever this VA is at, it is at a higher potential compared to this terminal. And how much will be the difference? The difference is E2. So this terminal will be at a lower potential, and it is lower by a value of E2. So this terminal is VA minus E2. So that is my another terminal of the resistor. So now the potential difference across that resistor is VC minus VA minus E2. Why it is VC minus? Because I have assumed the current in that resistor. I have assumed that it is flowing from VC to VA. So my VC is at a higher potential. So VC minus the other potential, which is VA minus E2 by the resistance, gives me the current in this branch. So this is entering and these two are leaving. So summation of leaving is equals to entering. Can we write VA minus E2 minus VC by R6? No, we cannot write because if I write VA minus E2 minus VC, then it means my current is flowing from VA to VC. So let me use a red color. So from whatever expression that you have written, it will be the current is in this direction, right? So if from a node, all the currents are leaving, then it means what? The summation of all the currents that are leaving or that are entering. Say if there is no entering path, currents are leaving, then it says the summation should be 0, right? If you agree. So according to your convention, VA by R1 plus current, all the currents are leaving, right? So it should be 0 plus whatever you have sent, VA minus E2 minus VC by R6 is equals to 0, right? Do you agree, whoever has asked, Pawan? Do you agree that according to your convention, this is the equation? Because whatever you have considered, currents are leaving. Yes. So now if you check, these two are same. If you clearly check, these two are same. Because if I bring this VA minus E2 minus VC, that's it, it will be the same. Just bring this onto the right hand side and you will get this equation. So the equation will not change. It depends upon your convention, because in your case you have assumed the current is flowing from VA to VC. In my case, I have assumed the current is flowing from VC to VE. Say by your method you got current to be in this branch to be 1 ampere. If I do in my way, I'll get minus 1 ampere. So that minus is the current direction is in the opposite. So it means whatever you have selected is the current direction. So first you have to assume the current direction, and then after assuming the current direction, according to the current directions, we have to write the KCL equation, because that decides whether the current is entering or leaving. If you mess up the directions, then you will end up getting wrong result, because if you are taking the current direction to be here, and if you consider this expression, then you are missing one minus sign, so you will be getting a wrong answer. So current direction you have to assume, irrespective of how I assume, we'll end up getting the same answer if we do according to our assumptions. So you are free to consider current direction in another way, and according to that way you can write the equations, and if you solve, we'll be getting the same answers. If our current directions are opposite, then if I get x, you'll get minus x. If you get y, I'll get minus y. Sir, why are you considering VA has higher potential in equation? Perhaps can we assume E has a higher potential or not? Yes, no, I am not assuming that VA is a higher potential than E2. I am assuming the current in the R6 is flowing from right side to left side. So I am assuming that R6, say this terminal Vx and this terminal Vy. So I have assumed that Vx is greater than Vy. I don't know about E2, I don't know about VA, I don't know about VC. I have assumed that current is flowing from right side to left side, which means my Vx is at a higher potential compared to Vy, and Vx is Vc and Vy is Va minus E2. Now, if you ask me whether Va minus E2 is positive or negative, that I don't know, because I neither know about E2 nor know about Va, but the expression is Va minus E2. So we have to follow the convention according to the assumption of our current directions. can we consider all currents leaving the node for VA, VB, VC? Yeah, you are free to consider the current direction. But once you have assumed or considered the current direction, you have to follow your convention and you have to write the equations according to that convention. In this regard, I would request all of you to consider one example. Say this example only. Assume E2, R6, R1, R2, E1. Give them some value. Say R6 1 ohm, R2 5 ohm, R1 3 ohm, R4 something. And now I have given all the values of E1, E2 and R1 to R6. Now you assume one set of currents and solve for VA, VB, VC. And now you assume another set of current directions and you solve for VA, VB, VC. You should get same VA, VB, VC in both of the cases. So when you consider two such scenarios for the same circuit, then you will know how they are getting the same thing. Because if you are considering the current to be opposite, where I am considering plus, you will be getting minus. But at the end of the day, we'll be both be getting the same voltage. So this will be a very good practice for you if you assume the currents and like for a given circuit, take two set of conventions and solve for the node voltages. So now we have solved for the node A. Now we'll go to node B. One thing I would say in a electrical course like network analysis, where there is a lot of math, the concept is simple, right? KVL, the voltages in a loop summation is zero. In KCL, the net current entering is equals to net current leaving. So the concept is simple, but solving the question in the right way without making any mistake is the most important thing. So it is majority of this course is math. So in such courses, you need to solve more problems. So you'll be more accustomed to all these calculations and you'll do less number of mistakes in the exam. We might know the concept. So if I have given you this circuit, I know the concept that I have to apply KCL at 3 nodes, but I should do each and every step without making any mistake so that I'll get the correct value. So it is about practice. The more you practice, the less you will be making mistakes. So I request all of you to solve as many problems as possible. I'm not sure if sir has given any reference book, or you can search some online problems and you can solve. So if you practice more and more questions, you will be making mistakes in the process. Then you will know where at what point you are making mistakes, so you can rectify them, and in the final assignment or exam you will not do that mistake again. So node B, I have assumed two currents are entering and one current is leaving. So what will be the value of this current?
VB minus VA by R2.
So again, whether it is VB minus VA or VA minus VB, I have assumed that
VA minus VB.
yes. So I have assumed the current. I am assuming that VA is at a higher potential. So VA minus VB by R2. One current entering and this current is also entering. So what will be this current in this path? Say this is VB.
Minus VB by R2.
So
R2.
so this terminal is VB. So this terminal will be VB minus E1. So I have assumed that current is flowing from 0 to that potential. So it will be 0 minus VB minus E1 by R3.
4.
So R3, I am considering R3, this vertical terminal. So this terminal is at VB and this terminal will be at VB minus E1 and this terminal is at 0. I have assumed that 0 is at higher potential compared to VB minus E1. So 0 minus VB minus E1 by R3. This is current entering. So summation of the current entering is equals to current leaving. How much is the value of the current that is leaving? VB. Value
VB
of the
minus
current.
VC by R4.
Yes, VB minus VC by R4. So this is the current at the node B. Now we'll go into node C. So node C, one current is entering and two currents are leaving. So what is the value of the current that is entering?
VB minus VC upon
6 minus
6
minus VC by
VB minus VC by?
R4.
Actually, this is VB. Sorry, if it looks like 6. VB minus VC by R4. Okay. This is the current entering and current leaving in this branch.
0 minus VC on R.
Or is it 0 minus VC or VC minus 0?
VC minus.
VC minus 0, right? Because I
VC
have
minus
assumed,
0.
yes, I have assumed that VC is at a higher potential. So my current direction decides that sign. Plus
Okay.
the current flowing in this path, which I have already calculated here, which is VC minus VA minus E2 by R6. So VC minus VA minus E2 by R6. So I'll have again equation 1, equation 2, equation 3. 3 equations, 3 unknowns. So we have three equations and 3 unknowns. Okay, so we'll solve for 3 equations. We'll come to how to solve these equations. So I'll check and I'll get back to you in the next week how to solve this. 3 equations, 3 unknowns. But in the case of nodal analysis, say I have given some circuit like this. Some circuit is like this. Okay, so I'll again consider the junction of 3 branches. Say this is VA and this is VB. So now I have 2 equations, 2 unknowns. But the issue here is, how will I know the current in this branch? I will not know, right? Do you agree? Okay.
Yes.
Yes. So in such cases, like if we talk from a mathematical perspective, in this circuit or in this network, I have 2 unknowns. So using KCL or KVL or some of them, I need to get 2 equations so that I can solve those 2 equations to get 2 unknowns. So now you are free to choose anyway, like you can choose any KCL or any KVL and you can get it. So one way is, say I can apply KVL in this mesh and I can apply KVL in this mesh and say this is 2 volts. I will get VA is equals to VB plus 2 volt. Or if I want to only apply KCL, say I want to apply KCL, in that cases, how will I apply KCL? That may be your question. So I will assume current I here, right? So at VA, terminal VA, I will apply KCL. Okay. At terminal VB, I will again apply KCL. Okay. Now how many unknowns we have? We have 3 unknowns. What are those 3 unknowns? This is 1, this is 2, and my current 3 is unknown. Right? And how many equations we have? This is 1, this is 2, and this is 3. So again, we have 3 equations, 3 unknowns. Because in this scenario, I will not know the current that is flowing through this voltage source. I have assumed that it is carrying a current I, and again, I have selected the direction to be from right side to left side. And now, as there are 3 unknowns, I have applied KCL at VA, which will give me one equation, KCL at VB, which will give me another equation, and VA is at higher potential to VB because they have connected the circuit in that way. And my equation says VA is equals to VB plus 2. So I have 3 equations and I have 3 unknowns. I'll solve. Sir, what is mesh? So mesh is like a closed path. So this closed path is one mesh and this closed path is another mesh. This closed path is another mesh. But within a mesh, there should not be any other mesh. Say I have considered this mesh. there are two meshes inside that mesh. So that is not a mesh. So mesh is a closed path within which another closed path is not there, which we use for mesh analysis. So till this point, is the concept clear for you? If you have any doubts, you may ask. So after this, we'll be going into the problem
Sir,
solving session.
V1 equal to VV plus 2V where come?
Okay, so this circuit is given to us, and the circuit itself is saying that this battery voltage is 2 volt. Okay, so VA is this terminal and VB is this terminal, and they have given the potential difference of this battery is 2 volt. So my VA is at a higher potential compared to VB, and this potential difference is 2 volt, right? So VA is equals to VB plus 2 volt. So that's how I got it from the circuit basically. Say if this is 3 volt, then I'll get 3 volt, 3 volt. Okay, so someone has asked what is mesh and what is loop. Yeah, nice question. Let me change the color to red color. So when I say loop, when I said the definition of the loop is like a closed path where if we are starting at a terminal, we should end at the terminal, and we should not cross the terminal again in between. Say, consider this path. Okay, this is a loop. But when we do mesh analysis, we cannot consider this loop as a mesh. Why? Because there are two such, which color? So there is another mesh here, and there is another mesh here. This mesh is also a loop. This mesh is also a loop. Right, because this is also a closed path. If we start at this point, we'll end at that point. If we start at this point, we'll end at that point. But when we say mesh, within a mesh, there should not exist another mesh. If I consider the outer loop as mesh, inside it there are meshes, right? So it is not a mesh. To be to say it in a easy way, so within a loop there can be another loop, but within a mesh there cannot be another mesh. Did it clarify your query, Yogita Jadhav?
Yes, sir, everything clear.
Okay, okay.
Yes, sir.
Okay, so there is again less than a minute, and after this, the meeting will be closed, and we'll rejoin this meeting, and we'll move on to the problem solving session. So just to summarize, till now what we have learned. So we have learned about the mesh analysis. So we have understood that we are using KVL, and we got equations. We have discussed about how to get the equations, and then we went to nodal analysis where we use KCL, and then we have discussed how to get the equations. Yes, you are right, Ram. All meshes are loops, but not all loops are meshes. Yeah, yes, yeah. To put in a better way, yeah, this is a better way to say. If this meeting can kindly rejoin, then we'll discuss about a few more problems. Yeah, if you have any queries till this point, you may ask. Hello, if you have any query, you may ask. I'm audible, right?
Yes, sir.
Okay.
Yes, sir.
Okay, so we'll take this assignment once.
You are audible.
Okay, okay. So let us take this question. I think this picture is not clear. Yes, so this is the picture. So in this picture, they are asking, the question is using nodal analysis, find V1, V2, V3. So they have given some voltages, predefined voltages, and using nodal analysis, we have to find V1, V2, V3. So how many unknowns are there in this question?
Sir, this is the image.
So how many unknowns are there? Are you able to see, or maybe I will assume it's
3 unknown.
3 unknowns, right? So how many equations we need?
3.
Yes. So we need to get 3 equations so that we can solve those 3 equations, and we can get the values of v1, v2, v3. So they said reference node. So they have told us we can consider this to be ground. Okay, let me use blue color. So now I have to apply KCL at each of these nodes to solve for v1, v2, and v3. So you tell me the direction. Here they have given current sources and they have given the direction. So you tell me in forums, how should I consider the direction, right to left or left to right? I'll go with the first
Right
person.
to,
So whoever says, I'll go with theirs.
right to left.
Right to left. Okay. And in 3 okay, if no one is saying, I'll assume left to right. And in 5 they have already given I, so I'll go with their convention. And 2 how should I consider, from bottom to top or top to bottom? You tell me any convention, we'll go with that way.
Top to bottom.
Top to bottom. Okay. So now we have assumed the current direction. So now I'll apply, so this, we are applying nodal analysis. So I'm writing nodal analysis.
Sir, can you please once said what is the role of reference node?
So reference node is, say, in a given circuit, we are calculating voltages. That voltage has to be with respect to some point, right? Like, say I'm saying V1 is 5 volt. I cannot say that 5 volt, like with respect to nothing. In our real life also, whenever we are saying it is of 10 volt, it is of 2 volt, we'll say with respect to some ground, right? We call it earth or ground. So with respect to some reference, we are saying this node is at this voltage, that node is at that voltage. So they're saying this is the reference voltage, which means whenever they say find V1, they're asking V1 with respect to this node. So whenever they're asking what is V2, they're asking what is the voltage of this node with respect to this node. So like voltage is a potential difference, right? Potential difference between two nodes. So one is the node where we want to measure the voltage. The other one is our reference node. So that's why they have said reference node. So with respect to this point, they're asking the voltages. So I have considered this to be ground, because if it is 0, then V1 is with respect to 0. V2 is also with respect to 0. V3 is also with respect to 0. I can also consider V1 to be reference node, but in the question they have told that this is reference. So I have to follow their convention. And also they have said the I direction is from V2 to ground. So I'm following their convention. In the branches where they have not specified anything about the direction, I'm free to assume my own convention. Yes,
What
somebody
about
said.
the correct direction for V3 from
V2
the
to
source?
V3. Yes, yeah,
Yeah.
yeah. So here also we are free to choose any direction. Say I am considering right direction. Say I'm thinking that that source is supplying, so I have considered some direction. But again, whatever I have said above, uh, it is a similar question, right? So there is a voltage source between two nodes, so I cannot apply uh, KCL here and KCL here. In such case, what I will do, I'll either assume current and then apply KCL, or I have to search if there is any other possibility. So we'll come to that point. We'll first start writing the KCL at node 1. So at node 1, so which is V1. Let me write V1. So the current entering is current leaving, right? So current entering, what are the currents that are entering? This is one current entering, and this is the another current entering. So 4 amperes plus what is the current that is entering? V3 to V1. So V3 is at a higher potential compared to V2. Sorry, V1. So what is the value of that current that is entering?
V1 minus V3 by 4.
Okay, and how are you saying that?
It's the V1 and V3 nodes were considered by resistance 4, no? So
Yes, which is at higher potential, V1 or V3?
V3. V3 is higher potential.
Yes. So the value is V3, right? V3 minus V1. Do you agree? Because the resistor is like this, and
Yes,
this
sir.
is at V3, this is at V1, and the current is flowing like this. It is 4 ohm. So the current is V3 minus V1 by 4, right? If you have any confusion, please free to ask. I'll explain it again. Should I explain again?
No, I got it. Thank
Okay,
you.
okay. So these two are the summation of the currents that are entering is equals to summation of the currents that are leaving. One current is the 7 ampere current and the other current is V1 to V2. So I will do 7 plus. So what is the current flowing through 3 ohm? You tell me now whether it is V1 minus V2 or V2 minus V1.
V1 minus V2.
Yes.
This is
you are
V1
right.
minus V2.
Yes.
V1 minus V2 by 3.
V1 minus V2 by 3. Okay. So this is equation 1. Now I need to get two more equations. So how I will be getting two more equations, that will come to it next. So can I apply KCL at V2?
Yes.
But I do not know the current in this 5 volt, right? So what should I do?
Can we say V3 minus V2 equals 5 volts?
Yes, yes, you are right. So that is another equation. It is not at any node. So V2, V3 relation I'm saving. We have V3 minus V2 is equals to 5 volt. Yeah. So now we have like 3 unknowns, but we got only 2 equations. So I need to somehow get a third equation. For that, I am free to assume something, or yeah. So any ideas what we can do? I need another equation, but yeah, like you're free to think. Like this is a circuit, right? It can be solved in n number of ways. I can say one thing, you can say one thing, but at the end of the day, either we'll go with the way that we have thought of, or we'll go with the way that is easiest, that will save the time. Because in such exams, we have to also save time, right? So we should solve this question within the limited time. So I need another equation. So there could be a number of ways. I can take one loop and I can solve, or I can assume this current to be I. So my unknowns will be 4. Then I'll get KCL here, KCL here. What I mean to say is, uh, if we go here, I have assumed the current I, right? And then I have applied KCL here, KCL here. So that is another way. What I mean to say is, I can assume this current to be I. So now I can apply KCL here, KCL here. So now I will get 4 equations, 4 unknowns, but it is very lengthy. I don't want to do that. So what else I can do? Any ideas? Any one of you like? If you have any idea, just feel free to say. Maybe it is whether we'll do that or not. That's a different thing, but you should not stop your thought process. So I need another equation.
How you consider the same current? I also in down and that.
Oh, sorry. That is a good thing. So this is some I1. It is not same current. Yeah. So this is some current I1 and this is I. Both are two different currents.
How about we apply KCL for reference node?
Yes, yes. Very good. Yeah. So we can apply KCL at the reference node. It is also a node, right? Yeah. It's a very good idea. So the current entering is current leaving. So these two are leaving, these two are entering. So what is the current entering this node?
I1 is entering.
V2 by 5.
Yes.
V3 by 2 equals to 2 and plus 4.
Yes. So now I have 3 equations, 3 unknowns. Okay. first I'll solve 2 and 3 because they are V3 minus V2. So let us use some different color. So from equation 2, I hope you are also solving, right? Or I should wait for you to solve because
No.
it's,
Please
yeah,
proceed, sir.
yes. Everyone should solve. This is not just me solving because you'll not gain anything if you see me solving. You will only get it if you solve it by yourself. So if you are not solving, please solve. Or maybe I'll just wait for a few more minutes for you to solve. I hope everyone has written these equations, right? Because if I go to next page, it will not be visible. So all of you should write these equations. Throughout this course, it's either me or my friend who will be teaching tomorrow. Irrespective of that, you should have a book and pen with you, and whatever we are writing, you should also write. So you should also try. Before I write, I ask you to do. So you should try something. So if you make a mistake, then you will correct it when I write the equation. So all of you should write. So can someone solve equation 2 and equation 3 and tell me what is V3 and V2? I'll wait for a few more minutes. You solve and tell me, then I'll cross check. And in the meantime, if anyone have any doubts, you can ask.
Sir,
Till this
V2
point.
equal to 5 volts.
V2 equal to 5 volts
Yes.
and V3 equals to
10 volts.
10 volt. Okay, yeah. Okay. I
Is
think they
it
are
right?
correct because substituting them satisfies that equation. So
That's
let
correct.
me, yes, okay. Equation 2 and 3. So from equation 2, I'll get V3 is equals to V2 plus 5. Substituting that in the equation 3, I'll get V2 by 5 plus V2 by 2 plus 5 by 2 is equals to 6. So solving this will give me 2V2 by 10, no, 7V2. Yes, let me solve this, then I'll explain the equation number 3. So 7V2 by 10 is equals to how much? 6 minus 5 by 2. So it is 7 by 2, right? Yeah. So my V2 is 5 volts and my V3 is 10 volts. So in the meantime, you solve for V1 and let me know what is the value of V1. In the meantime, I'll explain. So the circuit was given to us and we are to solve for V1, V2 and V3. So using KCL, I have applied KCL at V1 and I got equation 1. And as I have discussed before in the previous example, like this example, if there is a voltage source directly between two nodes, then I cannot apply KCL at this node and that node separately. Why? Because I don't know the current that is passing, right? So in such cases, we have to find some way to get another equation. So there is a voltage source between V2 and V3. So I directly got V3 minus V2 is 5 volt because they're connected by a voltage source, fixed voltage source. Now I have to get another equation. How will I get another equation? That I have raised the question for the students to think of a way where I can get another equation. And one of the student has said I can apply KCL at the reference node itself. So this another equation is KCL at reference node. So we can apply KCL because no voltage source is directly connected to another node at this reference node. So we said current entering is equals to current leaving. So current entering is V2 by 5 and current entering in another branch is V3 by 2 is equals to summation of the current leaving. Yes, V1 is equals to 2 volt. Can someone confirm whether they are getting V1 is 2 volt?
Yes, sir. V1
Yes.
is equals to.
Okay, then I'm not solving. I'm just directly writing V1 is equals to 2 volt. So now we got V1, V2, and V3. So we'll go back to our question and we'll see what is the question. I mean, what is the So this is a paragraph question. So it comprises of questions from 1 to 6. So once you solve this, you will be able to solve the sub questions. So question 1 says V1, what is V1? We got 2 volt. And there are two types of questions where they say range type. So when we say range type, there will be a particular range within which you have to write your answer. And if it is written in that range, you will get full marks, else you will not get marks. And there are other type of questions where you have to write the exact value. And if you deviate it from that exact value, even if it is a like say the value is 2 and you have written 2.01, still you will not be getting, because the type is not range. So you have to be very careful. Whenever there is a range, there is some flexibility to make slight mistake in the calculation, and still you will be able to score marks. Whereas in the case of other type of question where you have to write the exact integer type, then you will not be getting the full marks if you deviate it. Similarly, for V2, it is range type. So they have given a range. And what is the value of V2 that we are getting? 5 volts. So the range is given from 4.75 to 5.25. So within this range, if you write any value, you will be getting marks. Similarly, V3, we are getting 10.
Same value is accepted.
Sorry,
4.75 is accepted or more.
more than
Same value also is
4.75 to
accepted or in
5.25.
between.
That part I'm not sure. It depends upon how they have said. So I'm not sure. I'll again check and I'll get back to you. So I don't know whether it includes
Okay.
both the values. Yeah. Thanks for pointing it out. I'll check and I'll get back to you. Okay.
Sir,
And
I have
with
one doubt.
yes,
Sir, actually, in mesh analysis, we have written in some shortcut as the coefficient of the currents.
yes,
But is
yes,
there any shortcut to write down the KVL directly as the coefficient of
yes,
V1, V2,
yes,
V3?
yes. Actually, there in this lecture notes, there is that shortcut written for what do I say, this nodal analysis also. But as far as I felt, it would be like there will be some cases where you cannot apply nodal analysis, right? Say like here, if you see, we cannot apply KCL here and here, right? There are such extreme cases or some exceptional cases where we'll not be able to apply KVL. So whatever I have seen, like even if you learn to write it directly, it would be difficult in the case of nodal analysis because it is a bit complicated. So that's why I have not chosen to explain that. But if you want to explain, I can explain. But as far as from my experience, it is somewhat complicated with respect to mesh analysis. And if you forget or remember this logic in a different way, then you will be writing the equation in a wrong way and you will end up getting wrong results. So that's why I have told only one direct method. So in the case of mesh analysis, you will directly write the equation. Whereas in the case of nodal analysis, you can write the equation and modify here and there to get the equations. But yes, there is a way to write. And again, if such case exists, then either you have to transform it into a different circuit to apply KCL, or you have to think of some other ways. That's why I have not
Okay.
explained.
Okay, sir.
Generally,
Sir,
if
in
the
the
resistance
given
is
circuit,
having the current direction, then we can't able to apply any tricks over there. We have to consider the arbitrary and then we need to.
Yes. So like in this question, like they have considered the
They
current
already considered the current
Yes.
direction. So yeah, in this
Yes.
way, it is very difficult to apply
Uh,
the
uh, uh, uh.
tricks.
And also, I did not teach because the tendency to make mistakes in nodal analysis is more compared to mesh analysis. Because in the case of nodal analysis, as we are also doing, once we assume the currents, we have to follow that current convention. And if you mess up writing this equation, then you will end up getting a wrong result. So the tendency to make mistake here is more. That's why I have not told. Whereas in the case of mesh analysis, you always select clockwise, always. Even if they have given anti-clockwise current, you consider clockwise current. So whatever the answer they are asking is negative of what you got. So here it becomes very simple. So you are considering clockwise, and you can also apply KVL. So here it is easy to apply KVL also. Even if we do not know this, we can still directly apply KVL in this loops, and we can directly get. It's not always about how fast we do. It's sometimes about whether we are doing it in a right way or not. But I felt that in the nodal analysis, it is somewhat difficult compared to mesh analysis. So that's why I have not discussed. Yeah.
Sir, how can we know that whether to use nodal analysis or mesh analysis?
That is also another interesting aspect. So here in this case, if you see, let me choose a different color. So here, if I want to apply mesh analysis, so now I'll check how many meshes are there. There are n number of meshes, right? Say in this mesh, say consider V1, V2 ground. In this mesh, I am considering clockwise current, but I cannot apply mesh analysis here because I do not know the voltage of across this, but I'll directly get the current. Say this current is I1. I'll directly get current I1 to be 4. Then again, here I'll take one mesh. Here I'll take another mesh. Here I'll take another mesh. And in this, I'll take another mesh. You are free to select, but here, as the number of meshes are more, you will get more number of equations, and it might take more time. Whereas I can see there are 4 nodes. Out of 4 nodes, one node is ground. So there are only 3 unknowns. I need 3 equations. And out of those 3 equations, one equation is just related to only 2 nodes. So it makes my job easy. Probably in a different problem, mesh
Sir.
analysis could be easy. Yes.
Sir, current direction in register is not affecting it all. So I think nodal analysis, shortcut for nodal is it should be good for in nodal also shortcut.
Yes, like again,
What are restrictions?
Sorry, no. I'm saying there is this exceptional case when there is a direct voltage source connected between 2 nodes, then you cannot directly apply KCL because we do not know the current. Then either you need to transform it into the subsequent branches and do, or you can assume the current and apply KCL here and here. So you'll get one more additional equation and one more variable. That is one way to do. But in this given problem, we have found out that if we apply KCL at the reference node, it will make our job much easier.
Sir, I want to know what are the limitations of shortcuts of nodal analysis.
Okay.
Is there any limitations?
Yes. Not limitation in the sense, like there are no limitations, like they can be applied anywhere. Only issue, sometimes we might not directly apply. Okay, let me come back. In the case of mesh analysis, if there is a common current source in this mesh and in this mesh, we cannot apply KVL in this mesh because we do not know the voltage across this. Okay, let me write it using red color. So in this mesh M1, we cannot apply KVL directly because the voltage across this current source is unknown, right? Because I do not know the voltage across this current source. Similarly, if I apply KVL in this mesh, I'll again not know the voltage across this voltage source. So I am not getting 2 equations in this KVL and in this KVL. However, I know that I1 minus I2. So I1 is flowing like this and I2 is flowing like this. So I1 minus I2 is I. So this is giving me one equation. And in the mesh analysis, I am getting another equation. So I am only getting 2 equations instead of 3 because there is a current source that is common for 2 meshes, which is not allowing me to apply KVL. So in such case, I'll have to get another equation to get 3 equations to solve for 3 unknowns. So in that equation, I am considering the outer mesh. So in the outer mesh, I'll start from here and then I'll complete this entire path. There is no current source in this path, but I'll be getting third equation. Okay, so yes, this is the one exceptional case in mesh. Whereas in the case of nodal analysis, if there is direct voltage source connected between 2 nodes, say here we are considering this node to be ground. Okay, I'll use blue color here or dark blue. Okay, so I have considered this to be ground. Now if we directly apply
outer mesh one,
Yes.
that outer mesh one,
Mhm.
what will be the current taken?
Okay, okay.
So for
Yeah.
mesh 1 and 2, we considered I1, I2 and I3 for
Yes.
each mesh 3. So for outer mesh, what would be I?
Yes. So from our convention, what is the current flowing in this resistor?
I1.
Right? And according to our convention, what is the current flowing in this resistor? I2, right? And
Right.
according to our convention, the current flowing, the direction is also decided by the current direction that we have assumed. So this is I3. Got it. Say if I am applying KVL in this loop, then how will I know the current direction in this direction? So this resistor is having two currents. One is I1, one is I3. So I1 is in this direction and I3 is in this direction. So if I assume I1 is greater than I3, then I will say current is flowing towards right with a magnitude of I1 minus I3. Similarly, in this resistor, say I am assuming current direction to be here. It is also containing two current components. One is I2 in this direction and other one is I3 in this direction. Say I am considering this direction. So this current will be I2 minus I3. Understood?
Now regarding choosing the reference.
Without choosing the reference.
Sir,
Sorry.
I have a doubt regarding choosing the reference.
Okay.
Sir, if any figure it is shown that some point is grounded, is shown that it is grounded, dash 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 grounded, and then it is it necessary to take that point only as
Yes.
reference, or we can choose any other points as reference even if there is a given in figure that there is a ground?
Yes, yes. Yeah, good question. So the issue is, say, let us consider this question only. So in this question, they have said this node is reference node. So I have considered this to be 0 volt because they have asked in the question V1. So whenever they are asking V1, they are asking what is the voltage of, say, this is VA and this is VB. So my V1 is equals to VA minus VB. As VB is 0, it is VA, right? Now, what will happen if I choose some other terminal as ground? So if I choose V3 to be ground, then whatever voltage V1 you are getting, it is not just V1, it is V1 minus V3. Understood? Because whatever voltages we are measuring with respect to a particular point. So in the question, as they have mentioned V1, V2, V3, and as they are asking V1, V2, V3, the question is with respect to what node they are asking us. They have considered a reference node. So whenever they are asking what is the value of V1, they are asking VAB. So it would be good if you consider the convention according to the question so that we will not make any mistakes. Understood?
In this figure,
Uh-huh.
if V1 is grounded, okay,
Yes.
then I have to choose a reference. In such situation, can I left V1 and choose V2, V3 as a reference, V2 or V3 any other?
No. There is only one reference in the entire circuit. Reference is like a ground terminal.
If given is grounded, then it must be reference.
Yes, because
Is
like
it?
yes,
Okay.
like first question, we are free to choose any reference terminal to be ground. Or okay, let me just take a quick example. So okay, say this is 2 volt, this is 5 ohms, and this is 6 volt. So I'll take two parts in this question. The first part being this is ground. Okay. In the question, they have asked what is the value of VA, what is the value of VB. So can you tell me what is the value of VA?
2 volts.
2 volt, right? And what is the value of VB?
-6.
-6 volt.
Okay. So yeah, this is one set. Now I will consider another set. where I will consider this to be ground. Okay. So now what is VA and what is VB? VB is 0, right? Because I have considered this ground.
VA is
And
VA is how much?
8 volt.
8 volt. So now I'll ask you another question. What is VAB here and what is VAB here? What is VAB here?
Both
8
VA
volt.
and 8
8
Starting
volt, 8
from
volt.
B to
So
A. You used to start
in
from
both the
you start
cases,
your journey from B and go to A.
yes. So in both the cases, the potential difference across 5 is same. But in my part 1, I am asking the voltages with respect to this terminal. And in my part B, I am asking with respect to this terminal. So that makes the difference, right? But we are, see, if I ask the current in 5 ohm, my answer is I is equals to VAB by 5, which is 8 by 5 amperes. So if they have not specified any such ground terminal, half of you might have selected this, half of you might have selected this, but both will be getting the same current. But in the question, if they have given this ground, now the VA, whatever we are getting, will be different from the case where we are considering another terminal to be ground. So in the question, if they have taken a convention, you should follow that convention, else you will be getting wrong results. Understood?
Yes, sir.
Okay. And in the before this conversation, someone was asking border case in the case of nodal analysis where they cannot directly apply. So I have considered this example where I have considered directly a voltage source between VA and VB. So in such cases, I cannot apply KCL because I cannot get a expression of current in this branch. So in such cases, what I will do is one way is I have considered a current I, and then I'll apply KCL here and also KCL here. So now my entire circuit has 3 unknowns, mainly VA, VB, as well as I. So I need 3 equations. So one equation is directly the relation between VA and VB. The other equation is at VA I'll apply KCL, and the other one is at VB I'll apply KCL. So I'll get 3 equations, 3 unknowns. But let me get back to it. So the issue of learning these tricks is, say, here there is a trick for KCL, right? So they have given a trick for KCL, and they said that if there is a voltage source directly between A and B, then we can transform this circuit into some other different circuit, and we can apply mesh analysis. Okay, but there could be some questions like this where, or I'll directly go. There could be some questions like this where instead of transforming this voltage source, I could apply KCL at here, which will save me a lot of time, and it also simplifies my job. So it is not always to follow the tricks. The actual trick is to solve the question in an easier way. So it does not mean that you should always use mesh analysis, or it does not mean that you should always use nodal analysis. In the question, they're asking V1, V2, V3. So irrespective of any method I choose, I need to answer what is V1, what is V2, what is V3. So I will select my own way, or the easiest way in which I can solve this problem in a quicker way. So as they have said nodal analysis, I have applied KCL at V1 and I got a relation between V2 and V3. Now, either I could use the trick and I could transform this equation and then I'll apply mesh analysis. But I understand that it is a very lengthy way. Instead, I can think of another way where I'll get another equation. So someone said we can apply KCL at this point. So at the end of the day, if your question has 3 unknowns, you need 3 equations to solve. So I have to find a way to get the third equation. So in this question, I am applying KCL at this point to get the third equation. But it is not the only way to solve. That needs to be Understood. I can apply, I can consider any loop and I can apply KVL to get that third equation, but like it could be lengthier than this. So for a moment I thought which could be the easiest way to do, and we have realized that applying KCL at this point is easiest way.
Sir, after solving the question V2, V1, V2, V3, V3, after finding these values, if I verify at one of the nodes, does it mean my all three values are correct? Just to check whether my calculations are correct or wrong. So can I just only verify at a single node, KCL, and then I can be sure, rest assured?
Yes. So now now you got these voltages. Now you can apply, you can find the currents in individual branches also. So now you know currents in all the branches and voltages in all the branches. Now you can apply KVL in any loop, or you can apply KCL at any node, and it should satisfy, and it will satisfy if your calculations are correct. Yeah, so as we are getting closer to 8 p.m., I just wanted to summarize that we have discussed mesh analysis, which is all about KVL, and we have also discussed about nodal analysis, which is all about KCL. But there could be some border cases or exceptional cases where you cannot directly apply KCL or KVL. In such cases, you have to keep one thing in mind, that if your circuit has n number of unknowns, you need to get n number of equations. So there are n number of ways to get that equation, but it depends upon you how to get that equation. So you have to think and see in the circuit where we'll be getting that extra equation. Also, there is less than a minute, so if this meeting ends, kindly quickly join back. So if you have any further queries, we can discuss. Sir, please post PDF which you extract circuits into your Google Drive. Okay, actually that is previous year assignment PDF. I am not sure whether I can share it with you. I'll check with the course instructor, and if he allows, then I'll share. But whatever I have written here, this I will share, but that part I am not sure. If you have any questions, please ask, else we can end this session. Do you have any queries? If this meeting can kindly join back, okay. Hello. Tell me.
Here we have taken that V2, V3, and the current directions we have taken it in now.
Yes.
We can assume any arbitrary current directions. No, it doesn't mean that.
No. We are free to choose in any direction.
Okay. Generally, what happened is we have a simulation tool. When we check,
yes,
then we have to ground it properly to get the proper results. Maybe generally I have a habit of solving this and checking this circuit in network analyzers.
Okay.
When I compare the result,
like it should result in the same result, because let me just consider branding out of colors. Which color I will choose this? Yes. So if you are considering this to be ground, and even if you consider this in your simulation tool, then this V3, V2, V1 will be same irrespective of the current directions that you have assumed, and your simulation tool will should also show the same values. And the direction of the current, say I have assumed this in this direction. So say I got 2 amperes, then my direction is fine. Whereas in this case, I got -3 amperes, say for example, then it means the current is flowing in this direction with a magnitude of 3 amperes. In your simulation tool, it will directly show the positive current and its direction. But when we are solving the problem, we will not know in the beginning the direction of the current. So we'll assume with some assumption, we'll go with our assumption, then we'll solve. If we are getting positive, then it means our assumption is right. If we are getting negative, it means that we have taken in the opposite direction. But if in the question itself, they have given such assumptions like this, then you are not allowed to choose the direction of the current in that branch. You have to go according to that question.
Yeah, that's what we can't able to assume the current direction in our simulation tool, because it automatically takes.
It automatically does it. So it simulates and it will show
in
the
that case, we may end up with wrong answers. In simulation, I'm asking.
No, no, no. In simulation, like see, I'm saying irrespective of your assumption, you should get the same answer because it is a given circuit with given currents as well as given voltage source. So irrespective of your current direction, you'll get the same answer. Okay. Let me quickly take one small example. Okay. So I am considering a circuit. Okay, so I am considering a very simple circuit. Say this is 2 volt and this is 5 volt. So I do not know the current in the resistor. So I will take two scenarios where in the case one I am considering one logic and in the case two I am considering another logic. So in the case one I am considering downward direction and say the resistor value is 2 ohms. Okay, so yeah, now you tell me how to solve this. Any ideas? I'll apply KVL in this loop. I'll apply KVL in this loop. So in this loop, if I apply KVL, I'll get plus 2 minus 2i is equals to 0. Right. Actually, we are shorting two voltage sources. So let me.
Yeah. So technically it is wrong. If you can able to put one voltage source there, it will be okay.
I'll put another resistor here, say 1 ohm. So now 2 minus 2i is equals to 0. Okay. And what is the value of I?
It's 1.
1, right? So I is 1 ampere. So I got it. Now I need to know the current. Say this is I am assuming this one to be I1, right? Now I'll get here I1 minus I, right? Do you agree?
I1 minus 1.
I1 minus I or I1 minus 1, as we got I1 I equals to 1 ampere. So now I'll apply KVL in this second mesh. So I'll go from this point and I'll go in the clockwise. So 2I increment and then decrement minus 1 into I1 minus I plus 5 is equals to 0. Do you agree?
Okay.
Now I'll substitute I. So 2 minus I1 plus 1 plus 5 is equals to 0, which will give me I1 is equals to 8 amperes. Right. So 1 ampere here and 7 ampere is going there. Fine. Is that okay? Okay.
Yeah.
Okay. So 1 ampere is going here. So this is how much? This is 2 volt, right? And this is how much? Say I have considered this ground. This terminal will be minus 5 volt. So current in 1 ohm is 2 minus 5 by 1, which is 7 ampere. And it is exactly matching to whatever we got because I1 minus I is 7 ampere. So whatever calculations we have done, I have just cross-checked. So I is 1 ampere and I1 is 8 ampere. Now I'll consider in another scenario. I'll consider the same circuit. Okay, say 2 volt, 2 volt, 2 1 ohm and 5 volt. Okay. Now I'll consider the exactly opposite convention to whatever I have considered before. So here I have considered I am considering like this. Here I am considering like this. Here I am considering like this. Say this is my I1. This is my I2. So this is my I1 plus I2. Okay. Now I'll write the equations again. So what I'll be getting if I apply here, it will be 2 plus 2I1 is equals to 0. Sorry, isn't it? Do you agree?
So you are applying KCL to first loop, or
Yes, yes. In this loop, I'm going like this. So from here to here it is plus 2, and from here to here it is plus 2I1.
okay, two of okay.
Right?
Mm-hmm.
Okay. Now what is the value of I1?
1.
Or minus 1?
It's minus
Minus
1.
one.
Minus one.
Opposite, no? It is
Yes,
minus 1.
minus 1. Okay. Okay, so my I1 is minus 1 ampere. Now I'll apply KVL in this equation. I'll start it from here. So it will be plus or decrement. So minus 2I1 plus I2 plus 5 is equals to 0, right?
Same current direction you're taking, no?
See, from here to here, it is a potential, we are decrement, right? We are going to the lower potential. So minus 2I1 plus
Minus
I2,
2I1.
I2 into 1, actually I2 into 1 because resistor into voltage plus 5 is equals to 0. I have applied KVL in this.
Yeah.
So now if I substitute this, what I'll be getting? Minus 2 plus I2, so plus 2 minus into minus plus 5 is equals to 0. So I will say I2 is equals to minus 7 ampere, right? Then what is my I1 plus I2? Minus 8 ampere, right? So it says my current is in this direction with a magnitude of 8 ampere, or current is in this direction with a magnitude of 1 ampere, and the current is in this direction with a magnitude of 7 ampere, which is the exactly same thing we got in the previous case. So irrespective of the direction that we assume, we'll still be getting the same answer, and we should be getting the same answer. Is that clear? This point?
Yes. Yeah.
Okay. Yeah, so someone in the answer has said it should be 2I, not 2, but we got I to be 1 ampere, so I have substituted and I got 2I is 2. So I also request all the students to solve any given question in 2 different ways, considering 2 different current directions, but to see, then you will understand how the current direction changes your equation, but you will still get the same results. Whatever plus is there in case A could be minus in case B, but you will get the same results. There will be a negative sign if you have considered the opposite direction, which means the current is flowing in the other direction. But you should get the same answer. If you are not getting same answer, it means you have made a mistake. So you kindly check. I have randomly created one example and solved it to prove you, but you can take any other example in your assignment, whatever assignment that is there in week 1. You consider the same question, solve it in 2 different ways. By considering 2 different conventions, you will still be getting the same answers. Okay, then
I have a question related to. So, previously we have just reversed the terminals not to avoid the short between the two batteries, right?
Yes.
So, for example, if 2 different voltages are shorted in the given problem, let us say 2 volt and 5 volt, positive polarity and positive polarity are shorted, negative polarity and negative polarity are shorted. In between, we have some load. So in that case, technically, it is not possible to have the parallel voltage to be different.
Yes.
So in that case,
yeah, continue.
Or in between, maybe in parallel to that, maybe we have some load. Let us say some load resistance or load impedance.
Both will supply, at that time.
No, I'll come to that point. So yes, both will supply. That is one way of thinking. But say this is ground. What is this terminal voltage? I think
Sorry,
Ranjit
I'm unable
is
to see your screen.
okay. Ranjit, I think you are trying to write on my screen. Kindly erase it. I have to change that option. I forgot to change. From the next week, I'll change. Are you able to see my screen?
Yes, yes.
Yes. So I have considered this 2 volt, 5 volt in parallel and 1 ohm in parallel. So if this is ground, what is this terminal voltage?
2 volts.
2 volt. And what is this terminal?
5.
5 volt.
5 volt. But you cannot short to these. A single node
Correct.
cannot have two different voltages. So mathematically it says it is not feasible, but actually we should not short two different voltages. In reality, what happens is if I consider a 7 volt battery, and if I consider say 1.5 volt battery, and I consider some 12 volt battery, if I short both of them, then there will be lot of current
One
flowing
battery will
from one
act
to
like a load.
so a lot of current will go into the other battery, and it will be damaged. One of it or both of it will go off. So I'll tell you how. Say I have connected one battery. I have connected another battery with means of wire, but wire will have very finite resistance. A wire cannot be of zero resistance. Say it has some very finite resistance, say 1 milliohm, and this is a 2 volt. This is a 5 volt. So the potential difference across that very less resistance is huge. So there will be huge inrush current, and one of the batteries will be gone. So that's why we should not connect two different voltage sources in parallel, and mathematically also it is not feasible. So this is applicable to current source also. I cannot connect two current sources. So which law of KCL fails here? Sorry, which law of which Kirchhoff's law fails here? KVL or KCL?
Entering currents.
Here, in this loop or in this
KVL
circuit,
fails here.
KVL fails
Because
here
loop,
because in
total
this
loop
loop,
will be 0, na?
yes, it is not zero. Say I have considered two current sources in series, and there is another
If
resistor
it's so,
here.
then I think voltage drop will occur and the battery will drain.
Yes, the battery will be blow up or it will get damaged. Okay.
Is there any convention that higher battery will have internal resistance higher?
No, it depends upon the battery, like, what do I say, with what material it is made of. Some battery might have internal high resistance. It falls onto the architecture or whatever material they are using. So if one battery is lithium ion battery and other battery is lead battery, so both will be having different characteristics and both will have different
I mean to,
resistor.
I meant to say both are from the same type, let us say. So in that case, do we have any convention like that?
Probably we could say for higher voltage, it will have more on resistance if it is made of same battery, but we cannot
Just
actually
want to
say.
check that.
We have to actually go to the model of the battery. So each battery can be modeled using a mathematical model. So like if you study battery management in the future, then you will know. So each battery can be modeled using some mathematical model. So from that mathematical model, we would say, but yeah, depending upon that. So similar to voltage source, I have connected two current source. Now I cannot connect two current sources in series. Why?
Again, it is
Series,
violating KCL.
there is the current is same in series.
Yes.
And the two sources will define two current in same line.
Yes. So it is not possible. Also, if I apply, I'll say if I'm taking any node here, the current entering should be current leaving, right? So if I consider this node, current entering is 1 ampere here, and the current entering is also 2 ampere here. But it is not possible, right? It should follow KCL, right? Either the current entering should be equal to current leaving, or the total amount of current entering should be 0. So in the case of series connected current sources, KCL fails. In the case of parallel connected voltage source, KVL fails. So that's why it is not physically feasible also. You cannot connect it because one of it will get damaged. So we cannot connect two voltage sources in parallel, neither can we connect two current sources in series. One of KCL, KVL fails there.
Sir, I think it said in conclusion that voltage sources must be kept open circuited when it is not in work.
Yes. Also, we can say voltage source can be open circuited. Voltage source cannot be
That's it.
short circuited because again KVL fails and current source cannot be open because KCL fails. So it is always vice versa. So for voltage, it cannot be connected in parallel. So current source, it cannot be connected in series. Voltage, it cannot be shorted. So current source, it cannot be open. But it would be easy for us to think about voltage source because there are voltage sources available, but there is no ready-made current source. It has to be made using some circuitry, which you will learn in the future. But current source are not directly available in the market. So it would be somewhat difficult for us to think about it. But yeah, that is the case.
Sir, I have a last doubt.
Sir, any
Can
example
you
of
just go
current
to
source?
the
Okay, one at a time. Yeah.
Sir, any example of current source?
Yes. So in the example of, okay, you are asking me an example of current source. Actually, at this point of time, it would be difficult. But just remember that an inductor can act like a current source because in inductor, I can tell you. So in inductor, say
sudden
IL,
current is
there
not
is a
acceptable.
sudden increment in the inductor is not feasible. So it will have a lot of
Sudden change in the current can be acceptable because VL is equal to LDI by dt.
See, VL is LDIL by dt. So if there
Yeah,
is any
which
sudden
can
change in the current, it will be like an impulse in the voltage. So in
yes.
inductor, current cannot change immediately. It has to be a smooth function. Okay, so the inductor current cannot change immediately. So its current will change slowly. So in some scenarios, you can use inductor current as a current source because it more or less remains constant. You think about it, but it would be difficult for you to actually understand. But you can think uh, from capacitor point. Capacitor can be a voltage source, right? When it is fully charged, it becomes open and it is at particular voltage. Similarly, again, these two are like vice versa. So it is capacitor voltage that cannot be changed immediately, and similarly, it is this inductor current that cannot be changed immediately. This is one set of example. There is another set of example which comes from something called MOSFET. If your introduction to basic electronics is completed, then you might know about BJT, you might know about MOSFET. So MOSFET also acts like a constant current source. So in digital circuit, like if you take mobile phone, it contains digital circuits where they need constant current source, and they use these MOSFETs in particular way of connection. So their current remains constant. It's like the MOSFET is a 3-terminal device. Say this, they'll make it ground, and here they'll give fixed voltage. So the current in this path is constant. So they use this. So just remember that like there are no ready-made current sources. It has to be made from a circuit. So MOSFET is not a current source. MOSFET connected in a particular way can act like a current source, but it is also not ideal current source. In the sense, say I have a current source, I can short it and it still behaves like a current source. But whatever we make in the practical case, it cannot be shorted. Okay, so there are some like some limitations, but we can mimic and make a current source. Not perfectly, but yeah, realistically, in the realistic sense. You can think this is one example of current source, and this is another example of current source. But in the future, when if you are in the electrical department, you will be having analog electronics or some other electronics. where they'll be discussing about current mirrors. And in that case, the professor will be discussing about this current source, where MOSFET will be acting like a current source. Yeah. Okay, if you have no more queries, then we can stop here. And as I have said, I'll try to edit it and upload it by tomorrow evening also. And whatever notes this is there, I'll upload it to my Google Drive. We have the link. I'll also mention it in my YouTube video description. I'll add that link. But yeah, but I'm not sure whether I can share the assignments because they are previous year assignments. I have to talk to course instructor. Sir, can we have this recorded lecture of this after the session? Yes, I'll be uploading this to my YouTube channel, and I have mentioned the YouTube channel link in the chat. So if you go up, there will be my YouTube channel. So you can save that link. Also, there is this Google Drive link where I'll be uploading all the notes. So you save those two links, which will be useful throughout this all problem solving sessions. So I'll upload all the sessions in the YouTube by Tuesday night. So every week I'll try to upload, but if I am busy sometimes, it might be delayed, but I'll try to keep it as a habit and I'll try to upload it by Tuesday evening or night. Okay, with that being said, we can end this session. The link has been removed. Okay, let me just check it. I'll keep it again. Okay, due to the new chat. Okay, let me just quickly go there. I think the chat settings has to be changed. I'll change the settings so that our old chat will not be removed. Let me quickly edit link or copy link. Okay. Meeting group chat. Okay, kindly save this link as I'll be ending this session. You might not get the link again, but yeah, save that link and see you in the next session. Thank you, everyone. Thanks for joining.
Thank you.
Thank you, sir.
Thank you. Good night.